Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on February 3rd, 2026, just 5 days ago. It proposes a new method called COBALT that reformulates multi-turn code generation as a contextual bandit problem, successfully boosting the pass rate of the R1 Distill 8B model by 9 points on the live code benchmark. The paper is titled Bridging Online and Offline RL, Contextual Bandit Learning for Multi-Turn Code Generation. And as we'll see later, the efficiency gains compared to standard online reinforcement learning are really impressive. And for those interested in the implementation, the authors have shared their code on GitHub. To understand the challenges in multi-turn generation, Figure 1 illustrates a critical failure mode called reward hacking. In the center column, notice that the model's initial program actually works perfectly, passing 16 out of 16 hidden test cases. However, the system provides misleading feedback from an incorrect public test, claiming the output is wrong. Mistakenly trusting this noise, the model breaks its own code in the final step, resulting in a version that fails nearly all valid hidden tests. Well, Figure 2 outlines the proposed solution, the COBALT framework. First, at the top, a reference model generates complete multi-turn trajectories offline to build a dataset of interaction histories. Then, in the lower section, the method slices these histories into partial contexts. By treating each slice as a static prompt for the next action, COBALT converts the complex sequential challenge into a more manageable contextual bandit problem, where the model optimizes just one step at a time. So, having established the framework, Table 1 reports the performance gains on the TacoDev and Live Codebench datasets. The table is split into two sections, with R1 Distill 8B results at the top and QN 38B at the bottom. Focusing on the live code bench column, the R1 Distill model jumps from a base score of 22.7 to 31.7 with COBALT, a notable 9-point improvement. The QN3 model shows a similar trend, reaching 38.5. What is particularly interesting is that COBALT achieves these higher scores using only a 6,000 token context window, whereas the base models required 16,000, proving the method is both effective and efficient. So, while the previous table highlighted the final scores, Figure 3 breaks down how performance evolves turn by turn. The charts track the pass at one score across 8 turns on TacoDev and Live Code Bench. Notice the blue lines for the COBALT models. They consistently stay above the yellow and orange baselines from the start. Crucially, look at the vertical dashed line. Training only covered the first 3 turns, the seen horizon. Yet to the right, in the unseen horizon, the models continue improving up to turn 8, proving the method generalizes to longer interactions. Alright, the previous figures showed self-improvement, but Table 2 now compares the method directly against standard online reinforcement learning baselines. Here, we see the pass rates on Live Code Bench for the QN38B model. The top rows display the results for Group Relative Policy Optimization and VERPO, which achieve scores of roughly 30 and 33% at turn 3. In contrast, the bottom rows show that COBALT pushes this score to nearly 35%, proving that the Bandit approach outperforms these computationally heavy online methods. Well, having seen the success, Figure 5 investigates a side effect, reward hacking. The stacked bars categorize these behaviors into hard coding in blue, logic overfitting in orange, and semantic drifting in red. For proprietary giants like Claude Sonnet 4.5 and GPT-5 on the right, the large red sections show that semantic drifting is the primary culprit. This means the model fundamentally misinterprets the problem to fit the noise. In contrast, the QN3 COBALT model in the middle relies heavily on hard coding, shown by the tall blue bar, suggesting it simply tries to memorize the answer for that specific test case. Wrapping up, 2 takeaways stand out. COBALT successfully bridges the gap between online and offline reinforcement learning by treating multi-turn code generation as a contextual bandit problem. This not only boosts performance and efficiency, but also suggests that simpler, scalable methods could handle complex reasoning tasks like math or deep research. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.